Imagine, just for a second, that you are an engineer. You're standing on the street looking up at this towering skyscraper that's swaying, ever so slightly in the wind.
Right.
Then you look down at your phone, which is actively routing a mobile signal through the concrete canyons of a crowded city.
Mm-hmm.
Then you transport yourself to a factory floor, watching a robotic arm swing around to weld a car door with pinpoint precision. And finally, you put on your headphones, close your eyes, and just analyze the rhythmic structure of your favorite song.
Yeah, 4 completely different scenarios, right? I mean, different scales, different materials.
Yeah, actually, completely different purposes.
Yeah.
But what if I told you that stabilizing that massive skyscraper, routing that invisible Wi-Fi signal, moving that heavy robot arm, and mapping the groove of that rhythm are secretly the exact same mathematical problem?
It is one of those insights that fundamentally changes how you look at the engineered world around you.
Welcome to this deep dive. Today, our mission is to unpack a truly fascinating explainer document. It's titled The Geometry of Things: Engineering Applications of Euclidean Distance Geometry.
Such a great paper.
It really is. We have a stack of research, charts, and diagrams here, and our goal today is to figure out how engineers translate our incredibly chaotic, messy physical reality into elegant, solvable networks of mathematical distances.
Because that is exactly what they're doing behind the scenes.
Yeah.
They are using a unified framework to just boil down the physical world into pure geometry.
Right. And the core concept here, the beating heart of all this engineering, is something called the DGP engine.
The distance geometry problem.
Exactly. And the setup is remarkably simple. It takes an incomplete graph, just a web of a few known distances between scattered points, and it outputs their exact precise coordinates in space.
What's fascinating here is that this entire translation of reality is governed by a single foundational mathematical anchor. It is essentially the Pythagorean theorem on an epic scale.
Yeah.
The formula is just d squared equals the sum of xi minus xj squared. You are calculating the true distance between points in space.
Wow.
But this isn't just abstract theory living on a chalkboard. This specific geometry actively builds and dictates the engineered reality you interact with every single day.
I love looking at this like a giant spatial game of Sudoku.
Yeah.
You know how in Sudoku you sit down with a paper grid and you only have a few seemingly random numbers filled in?
Yeah, the givens.
Right, those are your known distances, and your job is to use logic to figure out the rest of the board. But here, the board isn't a flat piece of paper, it is three-dimensional space. You're figuring out where everything literally sits in the real world based on just a few initial clues.
And often those clues are incredibly sparse.
Totally. So if this is a giant spatial puzzle, let's start with a scenario where you are playing that puzzle literally blindfolded. You're trying to find your pieces when modern technology completely fails you. Imagine a network of tiny mobile wireless sensors scattered across a complex environment, like maybe tracking equipment inside a massive concrete hospital or deep underground in a mine.
This is a perfect starting point because it introduces the concept of self-localization. You have a fleet of devices that need to know exactly where they are. Now, your first instinct might be, just use GPS.
Right, just drop a pin on the map, let the satellites do the work.
But GPS is completely unviable here. It requires high power, which these tiny battery-operated sensors simply don't have.
Oh, sure.
And more importantly, GPS requires a direct line of sight to satellites in orbit, which you definitely don't have if you're indoors in a parking garage or, deep in a subterranean tunnel.
Right.
So these networks have to figure out where they are. They have to self-localize without any external map whatsoever.
And the mechanism they use to pull this off is wild. They rely on what engineers call anchors. These are just a few specific points in the network, maybe routers plugged into the wall, that actually do know their exact physical coordinates. But for the hundreds of mobile sensors wandering around, the unknown points, the system just guesses the distance between them based purely on radio battery drop-off usage.
It is a brilliantly pragmatic proxy for distance.
But think about how messy that is. Imagine you're in a pitch-black room with a flashlight. As you walk further away from a friend, the light gets dimmer to them. Radio signals work the exact same way.
Exactly, the inverse square law.
Right. The sensor sends out a ping, and it measures how much battery energy was drained to get that signal to the anchor. If the received signal is incredibly faint, the system estimates, okay, that sensor must be far away.
They're using energy loss to estimate physical distance.
Okay, let's unpack this. Because if you are just estimating distance based on something as fuzzy and chaotic as battery drain, the math must get hopelessly complicated.
Oh, it does.
I mean, radio signals bounce off concrete walls, people walk in the way and absorb the signal, batteries naturally fluctuate. If your distance inputs are just rough approximations, aren't the exact geometric equations basically intractable? How do you solve a puzzle when the clues are lying to you?
You are absolutely right to question that, and the underlying mathematics completely agrees with you.
Really?
Yeah. If you try to run those exact distance equations, like forcing the math to find a perfect microscopic point in space that perfectly satisfies all that noisy, bouncing radio data,
Hmm.
the problem becomes what mathematicians call non-convex.
Non-convex. Okay.
It is computationally intractable. It would require rank A. The algorithm just gets stuck spinning its wheels. It's impossible to solve in a reasonable amount of time.
So what did the engineers do? They can't find the sensors?
Not at all. This is where they use a brilliant mathematical trick called semi-definite programming relaxation.
Relaxation. I love that concept. The math is too stressed out trying to be perfect, so we just have to relax it.
Precisely. Instead of relying on a rigid equal sign in the equation, they swap it out for a greater than or equal sign. It looks like y minus x transpose x is greater than or equal to 0.
Okay.
They relax the constraints. Instead of saying this sensor is exactly 14.32 feet away, they say based on the battery drain, this sensor is probably somewhere within this general area.
And visually, instead of drawing intersecting lines that have to meet at a perfect microscopic dot, you end up with these overlapping fuzzy circles, right? They call them unit disk graphs.
Yes. You create an area of mathematically possible locations. By relaxing that equation, the impossible problem suddenly becomes convex, meaning a standard computer can solve it incredibly fast in polynomial time. It finds the overlapping shaded area in the middle of those circles and says, the sensor is mathematically right here in this puddle.
That's so clever. And this exact same fuzzy logic applies to exploring the deep ocean, right? Think about autonomous underwater vehicles, AUVs, fleets of submarine drones exploring the seafloor.
Right, because just like GPS fails indoors, radio waves do not travel through water. It completely fails.
So these submarines use time-dependent distance geometry. They send sound pulses to each other and measure the time delay to figure out how far apart they are. But ocean temperatures and pressures distort sound, so they use that exact same relaxed math to self-localize in the dark ocean.
They're mapping invisible, moving things through clever approximations of distance.
It is incredible, but let's completely flip the script. Finding moving invisible sensors is great, but what happens when the entire goal of your math is to make sure your object absolutely, unequivocally never moves?
That brings us from wireless networks to the realm of structural statics. Domain 2.
Building things that don't fall down.
Exactly. When you look at a towering structure, it is only in static equilibrium if its center of mass, its barycenter, undergoes zero linear acceleration and zero rotation.
Meaning it's perfectly still.
Right. Simply put, the sum of all the external forces pushing and pulling on it must perfectly equal 0.
And here, our distance geometry graph completely changes its physical meaning. In the Wi-Fi network, the dots on our graph were sensors, and the lines connecting them were invisible radio signals. But if you're building a suspension bridge or a skyscraper, the dots are the physical metal joints, and the lines connecting them are stiff steel beams of very specific lengths.
The external forces, like the crushing weight of gravity, a hurricane force wind, or a line of semi-trucks driving over a bridge, they push down on those physical joints.
Right.
Those forces try to compress or stretch the steel beams, but because the beams are stiff, they provide an equal and opposite reaction force.
Which resolves the stress. I was looking at the way they map the rigidity spectrum for these structures, and it instantly made me think of putting together cheap flat pack furniture. Like imagine you're building a bookshelf.
A very relatable engineering challenge for most of us.
Right, it's the worst. So the first stage on the mathematical spectrum is flexible. Imagine you take 4 pieces of wood and bolt them together into a square frame. If you push the side of that square, it just folds right over into a diamond shape.
It wobbles continuously.
Exactly. Mathematically, that wobbly square has an infinite number of ways it can fold. The geometry cannot hold its shape.
It has a continuous flexing displacement. The geometry is failing.
Then you get frustrated and you grab one diagonal cross brace and nail it right through the middle of the square, connecting 2 opposite corners. Suddenly it locks. The frame holds its shape. You have reached the second stage, infinitesimally rigid.
Yes. And structurally, what you've done is complete the rigidity matrix. Once you add that diagonal brace, The internal shape cannot flex anymore.
But there's a catch, right?
There is. The only mathematical solutions left for the structure are translations or rotations, meaning the internal square is locked, but you could still slide the entire thing across the living room floor or spin it in a circle.
Which you definitely do not want a skyscraper to do.
No, you do not.
So, the ultimate goal for an engineer is the third stage, globally rigid. This is the holy grail. A unique realization of the math that locks the structure into one singular possible shape, completely independent of edge weights.
And that is the crucial hidden insight here. Structural integrity isn't really about the physical materials themselves.
Really?
Yeah. I mean, you could use the strongest, most expensive steel on the planet, but if your geometry is flexible, the building will fail. Statics is entirely about ensuring the geometric distance constraints between the joints perfectly resolve the stress. The material is just there to enforce the math.
Wow. Okay, so far we've used this underlying math to map physical space with invisible radio waves, and we've locked physical steel beams together to fight gravity. We are dealing with real, tangible space. But what if we aren't dealing with physical space at all?
It is a big shift.
Yeah, what if the space we are mapping is abstract human knowledge?
Now we are entering domain 3, the world of data science and dimensionality reduction.
The core problem here is that human decision makers are physically, biologically limited. We simply cannot visualize high-dimensional data relationships.
Okay.
Like if you're a medical researcher looking at a spreadsheet with 50 different columns representing 50 different health variables for thousands of patients, that is a 50-dimensional space. Our brains literally cannot picture that.
No, we need it translated into a low-dimensional space. We need it squished down to 2 dimensions on a flat computer screen, or maybe 3 dimensions, where our human eyes can actually look at it and spot the patterns.
And the solution engineers use is called multidimensional scaling, or MDS. You start with this massive high-dimensional database. The algorithm calculates a dissimilarity matrix, which is really just a massive list of how mathematically different every single patient is from every other patient across all 50 variables.
Exactly.
MDS takes that massive web of abstract differences and constructs points on a flat 2D graph, ensuring that the physical inches between the dots on your screen mimic those complex original relationships.
It creates a physical, visual approximation of completely abstract data using Euclidean distances.
But wait, so what does this all mean? If we are squishing massive 50-dimensional data down to 2 flat dimensions, aren't we just severely distorting the truth? We have to be losing so much information. How is this any better than principal component analysis, or PCA, which is the standard tool practically every data scientist uses?
This is a phenomenal question. And if you look at the algorithm comparison chart from the source material, it gets to the heart of what truth means when you compress information. PCA and MDS have completely different philosophies.
Okay, break that down for me. How do they differ?
PCA uses spectral graphs theory, and it is driven by maximizing variance. Its core goal is to capture the biggest overall spread, the grand shape of the data. Think of it like taking a complex 3D object and shining a flashlight on it to cast a 2D shadow on the wall. The shadow captures the broad outline. But the danger there is that PCA might take 2 data points, say 2 patients, who are actually very different in the true 50-dimensional space, and project their dots right next to each other on your 2D screen just to preserve that overall massive shadow.
So PCA essentially lies about the local point-to-point distances just to make sure the big picture looks nice and spread out.
Exactly. It sacrifices local truth for global shape. But MDS is driven by distance geometry. Its core goal is to preserve the actual the underlying dissimilarity metric itself.
Okay.
Even if the overall global shape of the data gets completely warped, MDS actively fights to make sure that if 2 patients were mathematically far apart in the data, their dots stay physically far apart on your screen. It treats the data relationships as physical laws that cannot be broken.
That is a massive aha moment. MDS is treating abstract data as if it were physical distance. A difference in a spreadsheet literally becomes a physical gap on a graph. It is intentionally manipulating space to show us the truth.
Yes, exactly.
Now let's take that intentional manipulation of space and apply it to an active, moving machine.
This takes us into domain 4 robotics, specifically the inverse kinematic problem, or IKP.
Imagine you're standing next to a massive robotic arm on an assembly line. This is where our distance geometry graph shifts its meaning once again. The known dots are the hinges and joints, and the rigid lines connecting them are the titanium segments of the robotic arm.
The knowns in this problem are the fixed bone lengths. You know exactly how many inches long the robot's mechanical forearm and bicep are, and the physical constraints of its joints.
And the unknown is exactly what coordinate values all those intermediate joints need to have so that the final node, the hand or the welding torch, hits a very specific target destination in space. I was trying to visualize this, and it's exactly like trying to touch a specific fly on the wall while blindfolded. You know the exact rigid length of your upper arm and your lower arm. But to hit the fly perfectly, you have to mathematically calculate exactly how much to bend your elbow, twist your wrist, and rotate your shoulder simultaneously.
And if you look at the geometry of that movement, the movement envelope of any joint forms a perfect sphere in three-dimensional space.
A sphere. Okay.
Yep. If your shoulder is locked in place, your hand can only move along the outer surface of an invisible sphere. When you bend your elbow, that creates a second sphere interacting with the first one.
So it's just spheres intersecting spheres.
Yeah.
But how do the roboticists actually solve for the exact angles needed? I mean, unlike the Wi-Fi sensors where we just relax the math to get a fuzzy puddle of probability, a robot needs absolute precision.
Oh, absolutely.
If the angle is off by a fraction of a degree, it smashes through a car windshield instead of welding it.
They need guarantees, not approximations. So instead of relaxing the math, they use algebraic geometry to reduce polynomial systems, and a technique called interval analysis, which relies on a method known as branch and prune.
Walk me through how branch and prune actually works.
Imagine drawing a giant invisible box around the entire physical reach of the robotic arm. You know the exact coordinates to hit the target must exist somewhere inside that box.
Okay, I'm picturing the box.
The algorithm branches by cutting that giant box in half. Then it mathematically evaluates both halves. It actively prunes or deletes the half where the geometry proves the arm simply cannot bend.
So it literally just throws away the impossible space.
Exactly. Now you have a smaller box. You cut that in half again. You prune the impossible side. You keep carving away the empty, impossible space, iteratively dividing and deleting until the only thing left remaining is the microscopic, exact mathematical coordinate the joint needs to reach.
That is so elegant.
The versatility of this underlying geometric framework is what makes it so incredibly powerful.
It really is. We've gone from Wi-Fi networks in dark tunnels to steel bridges fighting gravity to squishing abstract data to programming heavy machinery. But the sources hint at frontier applications that go beyond physical space entirely, things that bleed into time and even into art.
This is where we truly push the boundaries of what this math can do. Let's consider clock synchronization.
Wait, how does the flow of time fit into distance geometry?
Mhm.
We've been talking about millimeters and miles.
Because to the pure mathematics, a distance is just a constraint between 2 points. Synchronizing network computer clocks across the globe is essentially a one-dimensional distance geometry problem. It's actually the only major engineering application of 1D DGP.
Oh, wow.
They synchronize these massive networks by using the time offsets between pairs of clocks as the distance. The math fundamentally does not care if the distance constraint is measured in meters of steel or milliseconds of time. It just solves the missing edges.
That is mind-bending. Time itself can be mapped as a one-dimensional spatial puzzle. And then there is what the researchers call the geometry of music. You can actually perform a quantitative analysis of music by abstracting rhythms and musical timing into distance matrices.
You are quite literally mapping the temporal distance between beats.
Yes. You can find structural, quantitative similarities between two entirely different songs by mapping their rhythmic distances. You treat a drum pattern as a geometric shape. It's quantifying the groove of a song into physical space.
If we connect this to the bigger picture, you have to look at the synthesis matrix in the source text and the grand abstraction of all these fields. We have massive suspension bridges with physical crushing forces. We have Wi-Fi routers emitting invisible radio signals. We have autonomous submarines dealing with sound delays in the ocean. And we have robotic arms with rigid titanium joints.
But in the pure distance geometry abstraction, all of that tangible physical reality, it completely vanishes.
Exactly. The crushing gravity, the radio frequencies, the stiff metal, they all disappear into pure mathematics. They just become positive semi-definite matrices and Cayley-Menger determinants. The knowns, whether that's a fixed physical beam of wood, a draining battery, or a temporal delay, just become the variable d for distance.
Right.
And the unknowns, the reaction forces, the sensor coordinates, the robotic joint angles, just become the variable x.
It is the ultimate takeaway from this entire exploration. Absolutely everything is a network of distances. Whether you're an engineer stabilizing a skyscraper or a roboticist programming an assembly line, Your job fundamentally reduces down to solving the exact same geometry problem. Every single physical constraint in our engineered reality is simply a missing edge in a Euclidean distance space.
It provides us with a beautifully unified theory of physical problem solving.
Think about that the next time you connect to a Wi Fi network in a coffee shop, or drive your car over a suspension bridge, or even just tap your foot to the rhythm of your favorite song. You are interacting with and entirely relying on the exact same invisible geometric web. It is all the same math running silently in the background of reality, holding our world together.
And this raises a deeply profound question. A final thought for you to ponder long after we sign off.
Let's hear it.
We've seen today that distance geometry can map rigid structures, moving robots, abstract human knowledge, and even the flow of time itself. If every physical and abstract constraint in our engineered world is just a missing edge in a mathematical graph, could our incomplete understanding of the universe's biggest, most terrifying mysteries, like the location of dark matter or the mechanics of quantum gravity, simply be an incomplete geometry problem waiting for us to find the right vertices?
Now that is something to think about. Thank you for joining us today to unpack the hidden geometry of our engineered reality. We will catch you on the next deep dive.